So my name is Adam Crane. I'm a software engineer in the SCADA automation kind of power area. I've been doing that for about a decade. So I guess, Sergey said this talk is about the systems that keep the lights on. I guess I'm the software engineer that writes the bugs that turns the lights off. And the protocol we're going to talk about is called DNP3, and it's actually an IEEE standard as of about 2010 or 11, I think. So I want to assume that people know too much about SCADA, so I'll give you a really quick rundown. SCADA is kind of a subcategory of all industrial control systems, and the characteristics that make it SCADA are generally a couple of things. They're geographically distributed, so you're monitoring some process that is over like maybe a large span of areas. You can think about the systems that kind of monitor all the electric substations you have in the field, or maybe you're managing water flows in a water system. And it's the communications are generally hub and spoke and centralized. So you have some kind of control center that's really trying to monitor all the things that are going on in the field. And for the most part, those processes are able to kind of protect themselves over the short term. There's some kind of logic distributed out in the field, and this communication may come and go based on, if a storm comes in, you need your things to kind of be able to keep things going in the absence of that, supervisory control. But, because these things are geographically distributed, they use all manner of communication technologies to get out to those remote endpoints. So you may be surprised to learn that like a large portion of the communications infrastructure for the electric power grid is still over 1200 baud modems, for instance. And most of the protocols in this space were designed to work over those sort of legacy serial networks, and now have been kind of transformed, and maybe they've added encapsulation, or maybe they've removed it, and now it's all being kind of put over bare TCP. DNP3 was kind of a first in this area. If you were in electric power kind of in the early 90s, mid 90s, you bought like a monolithic solution stack from one vendor and they gouged you for it, and you had no ability to pick other equipment or things from different vendors. So it was kind of a first effort to say, here's a standard, all the vendors will implement it, people can pick and choose, and just really was an attempt to kind of avoid vendor lock-in. But like many standards, people couldn't resist the urge to add things to it, and things kept getting bolted on and bolted on and bolted on. This is not your grandma's RFC. This thing has about 1,200 pages to read through if you go and download the specs. So we have a few people in this room that I know have looked at encoding different levels of this protocol in toolkits like Hammer, and they can tell you it's not simple when you start going through all the different possible encodings and data types. And I think as Meredith said at S4 a couple of years ago, it's deeply into context-sensitive territory, and also has an enormous amount of state. So implementing this is a real problem, and doing it securely is, I don't know if anyone's going to be able to do it reasonably. Quickly over the architecture of the protocol, like I said, it's a legacy serial protocol, so it has its own link layer with CRCs for error correction. It has a very crude transport layer that does kind of in-order reassembly. So you'll get messages here that are about 300 bytes, and multiple ones of those accumulate in the link or transport layer reassembler up to an application layer message that is usually no bigger than about 2K. And at that green application layer, that's where your SCADA semantics are. Things like control messages to open a breaker or open a valve or turn on a pump, and data back from the field. Measurement values like, a binary is a breaker open or closed, or, what's the reading for current or voltage on a line. So at a very, very high level, application layer messages look like this in DNP3. You've got a function code, and then you have 0 or more object headers that follow. And the encoding of this is highly irregular and depends on the different types of, header types that you have there. And then, so the semantics of the messages themselves are really a combination of function codes and objects. And the spec doesn't really say, it says which you're allowed, but it placed no limitations on all the different permutations of objects that you can pair with function codes. So you can do all kinds of operations in a single message because the meaning of those function codes is very overloaded. So a write means completely different things. You know, are you writing the time and date? Are you trying to do a time synchronization? Are you doing a write to actually open or close something? Are you writing a file? Well, you can do all three in one message, right? So there's very little constraint placed on the messages, which makes validating these and figuring out what to do with a single message not so easy. It's also made it very easy to kind of extend the protocol. So I got into this because I was working on an open source implementation of this protocol and kind of got interested in fuzzing. So I wrote a smart fuzzer, and I had a buddy at an electric utility who just kind of unleashed it on everything in his lab. And he's like, it's all broken, right? And somehow, I don't know how he did it, he got the permission of his CIO to start reporting to DHS. So he went on a massive bug campaign in 2013, just kind of fuzzing everything we could find. And we ended up with, like, you know, about 30 different CVEs coming out through ICS cert. And as far as this LangSec goes, it's kind of a really deep study of all the different failure modes that you could see in one protocol. We have a nice assortment of different things. So you can go to that link and kind of look at all the different CVEs. They're not terribly descriptive. There's a real stigma around releasing ODAs and ICS SCADA. So we released, I'll tell you some stories in the hallway about interactions with vendors, but we released some of the data, but we never tied it to a specific product to give people an example of what frames cause failures. You didn't want to embarrass anybody, and I didn't want the FBI showing up at my doorstep. One of the things that was kind of an important revelation for the industry was kind of a different attack vector. In electric power, things are primarily kind of compliance driven. People aren't, if you're on the network, you're on the network. So most people, from a compliance perspective, are really worried about that bridge between the corporate network through the DMZ onto the OT network. They're really worried about, you know, protecting that as an attack path. But what we showed was that you could go out to some kind of remote site in the field, you know, and doesn't have a camera, and send fuzz packets back toward the control center. The control center really is a server platform that's talking to hundreds of things. So if you knock that thing down or you tip that thing over, operators have lost control or visibility to their entire system. And also, there's an exception in the regulations for what you have to do for serial communications, since they're non-routable. It's much easier for utilities to, they're exempt from NERC-CIP regulatory requirements. So showing people you could send the same fuzz data over 1200 baud modem or 900 megahertz radio and have the same effect was kind of a revelation for them. And you probably think it's silly, you know, parsers are parsers regardless of how they're consuming the bytes, but they thought that was kind of a big deal. The fuzzer itself, like I said, really nothing special. It was just a generational smart fuzzer. Having implemented the full protocol, it had a lot of insights into, you know, where people would likely make mistakes. So it was easy to kind of capture those. A lot of the modeling was really just stressing integer boundary conditions and overflows and adding or removing, you know, expected data. And, you know, we didn't have source code for these things, so we couldn't do instrumentation. So we had a very, very simple, you know, failure metric, you know, send a known valid packet, get a response, try another attack packet, do it in a type loop till the device stops responding. And I'm sure we missed all kinds of subtle things like memory leaks and so forth, but there's, you know, so many seg faults that, you know, it doesn't really matter. You know, like I said, what did we find? You know, I don't have any videos of bricking the embedded devices, but, you know, just a few screenshots of Windows things. There were, you know, a lot of infinite loops that allocate memory till the process bleeds out. A lot of, you know, a lot of read access errors, a lot of buffer overruns. I mean, I'm not a reverse engineer. It would have taken a long time to go and try to reverse every single one of these. So, you know, sometimes the language runtime tells you it's a buffer overflow. I can get that right. Some of the common faults, most common, DNP3 has these header types called basically start stop. They tell you that there's basically an array that follows with a certain number of like fixed length elements. And these are just addressing for the different measurement values is done completely by index. So this header type basically says there are measurement values from 0 to max unsigned int of a certain type, of a certain fixed length type. So to actually validate that header and move on to the next header, you have to figure out how many there are. Well, you know, you do this, you're going to have an integer overflow, and when you end up reading the data, you're going to end up crashing with the read access errors. That's going to roll back over to 0, right? So that was, you know, extremely common fault. You know, but even more interesting, I think, were some of the kind of less common faults. This is actually a reply message from a remote device in the field back towards a master. And the object type that it contains is a control that should normally go in the other direction, right? So this would never come from the field back towards a master. And it's completely syntactically valid. All the data is, all the specified data is there. It's just semantically meaningless. Because that, you know, it's an example of something that should never make it past a very, very early stage of parsing or whitelisting. And even more interesting, the buffer overrun was only triggered if those last two fields of 11 bytes were particular values. So we were kind of seeding those with pseudo-random data as we were fuzzing, and it took particular combinations to trigger that. So something had gone pretty horribly wrong in the early stages of processing on that one. So, you know, a lot of people said, you know, so what? This is an unauthenticated protocol, right? What's the point of fuzzing something that has no auth? You can just trip and close the breakers. Well, the committee since 2007 that designs this protocol has been adding security into this protocol. So not on top of, but actually into the application layer itself. And it's really tightly coupled to the application layer. They've invented new function codes, new objects, new state machines, and they have two modes of authentication and some really cute things for like saving bandwidth. So I would say that a lot of the things that they've added to this really, really complex protocol, I'd go so far as to call them, you know, security anti-patterns. The first one is they have selective authentication. So they basically take in the space of all the different function codes in the standard and try to identify the ones that they deem critical. And that's mostly oriented around function codes that could affect the process state, like opening and closing a breaker or reading and writing a file. But you'd be surprised to learn that responses coming from the field are non-mandatory. You could enable challenging and authenticating those responses, but you're not required to have them on by default. And it's interesting, if you do a crude analysis of the protocol itself, responses from the field with measurement data can be paired, those function codes can be paired with the highest number of objects. So they have the highest attack surface. So the people that designed this protocol really, there was no thought to protecting from implementation defects. It was all oriented around you know, having perfect parsers, assuming a world of perfect parsers where these bugs don't exist, and just kind of protecting what the function codes actually do for the process itself. So there's a couple other kind of gems here in the standard. Two modes of authentication. The primary mode is challenge response, which nobody likes because it adds a bunch of latency on these systems that can be time critical. So, you know, you send a message, the outstation or the master says, you know, prove it's you, here's a nonce, you know, produce a hash for me, send it back, okay, and then you process the initial message. You can actually implement that reasonably well because you can kind of treat that blob after the function code as an opaque set of bytes, not even touch it until after you've gotten back your response to the challenge and validated it comes from a trusted source. There's another mode called aggressive mode, which is kind of a one-pass authentication. And that mode uses sequence numbers to protect from replay attacks. So what they've done is they've reused the normal DNP3 object headers, and the payload objects that would normally be part of a normal request are kind of sandwiched in the middle there. And it's preceded by a user ID and a sequence number that has to increment, and then the HMAC is on the end. But, you know, like we've already discussed, there's Well, first off, there's an ambiguity with the request itself. You get a message like this, and you have a function. There's no special function identifying this as aggressive mode. So you have to speculatively parse the first object header to even determine whether it's an aggressive mode or a normal request. So they've already added some new syntax that's completely different than the old protocol just to handle this use case. That's not great. It's not so bad. The thing that I'm a little more worried about is that this kind of pseudo envelope, you can't parse the object, you can't skip object headers. You have to at least do some level of light parsing to get to the HMAC at the end. So you're actually having to inspect this potentially dangerous data just to authenticate yourself. It's irrelevant. You don't even want to process it until you've gotten to the HMAC at the end of the message. Fortunately, after the session key negotiation, you know how big that HMAC is supposed to be. So if you know what you're doing, you can try to rip it off the end, validate the message, and then do some parsing. But that's not documented anywhere in the spec, and I suspect it's the kind of thing that will trip a lot of people up. Other gems. So some of the objects themselves that encode some of the security primitives. This one is a session key status object. This is how the one side notifies the other the state of the session keys. How they're encoded, this object is usually framed by tag length value, so there's a header that specifies the size of the whole object. And these objects have some number of, oh, it's not a laser pointer. But there we go, some number of fixed length fields. The fixed length fields always come first. And then some number of variable length fields. So in this object, the way that it's encoded is they have a 16-bit integer that frames this sub-variable length field, and then the last variable length field is implicitly the remainder from the encapsulated framing. Not great, right? Well, you would think that they would at least apply this encoding scheme consistently. Some of the objects have explicit length for this field that can disagree with the framing. So it's done in two ways. Well, what does the spec have to say about this? You can just read that second part. It says, the length of the challenge data may therefore be either calculated from the qualifier or read from the corresponding field of the object. It'll be fine, right? No, that's not good. So these are the kind of things that need to be cleaned up. These are where modeling protocols and grammars will have a real impact, and these are the kinds of things that will be a significant source of bugs, I think, for implementations of this protocol going forward. It hasn't gotten a whole lot of adoption yet. I mean, this feedback is definitely kind of going towards the committee, but they do have devices in the field, and changing this are breaking changes. And with the patch situation in SCADA, it's really a nightmare to roll updates to things. So, conclusions on SA. I really think that SCADA vendors should really just consider a layered approach. Don't try to get cute and selectively authenticate based on function. Data is dangerous regardless of what the intended function is. I've really been trying to sell that message to people. How can LangSec help? I think we need better tools. So I like hearing about stuff like Hammer, the Rust parsing library. We need those tools to work on embedded systems. So we need variants of those tools that can handle things like deterministic latency. Standards bodies need some theory and guidance to produce better designs. Participate if you can. And a trap I've seen over and over in this space is I think that as they develop these protocols, they need reference implementations to kind of inform that. People spend an enormous amount of time in these committees, and it's mostly consultants kind of writing things on paper and then just hoping it's implementable with very little feedback. So I think that's really important. That's kind of where I've been trying to help. With that, that's questions. I know there was a lot of things in a very short period of time, but.
Thank you, speaker. So distinctly not a theoretical problem.
No.
Questions?
Thanks. One thing that jumped out at me here is perhaps not intimately too related to LangSec, but do you know of any ways that the aggressive mode authentication in particular is currently being protected against replay?
Besides the sequence number?
Oh, it does have a sequence number.
Yeah.
Okay.
And they use the sequence number even in the challenge response, so it's like, somewhat unnecessary, but there's no timing protections in aggressive mode, so you could definitely hold a packet back and then replay it at inconvenient time, so it's somewhat less secure than the challenge response, but yeah, it's just a 32-bit sequence number.
More questions? In that case, let's